73. Right, I think it's half of them not yet joined, but it's okay. So we are short of time, so we will just start anyway. Let me share the screen. Okay, so very good morning semua. So hari ini kita akan buat the last final revisions for final exam, for tomorrow final exam, right? I will go quickly. From the beginning until the end, right? Maybe we don't have much time to stop for any uh, problem solutions or anything during the lecture. I will go through quickly for each of them, each of the topic which included into the final exam. Um, so so you have to try some of the questions after that. Is up to your initiative to try some of the calculations, some of the theory to strengthen up all uh, the fundamental after the class, right? Okay, we review a little bit again on the topic from the final exam. I'm trying to give as much details as I can, provided that I don't expose the whole questions, right? 100% for the final exam. Questions one is objective. We cover from the electrostatic until EM wave propagations, right? So 10 objective questions with each of them 2 marks. So make it total 20 marks. So each of the questions, 5 questions is compulsory to answer. Each of the questions is 20 marks. Then when you add up, total will be 100, right? For second questions, you will see we have 3 parts. So you can expect that if the marks given is 3 marks, then the calculations is quite short. Then easily you can get the answer, right? If the calculations is given to if the calculations given to you is 9 marks or 8 marks, means the calculations need quite some step in order to achieve the answer, right? So you can expect from here. For those theory also same, right? When I say theory, means you need to elaborate, you need to give some discussions with respect to the theory given, right? You can put it in the point form, but you can expect what I expect from 5 marks over here, right? Theory is not much in the questions unless in the first question, first multiple choice questions, we have quite a lot of theory, right? The theory is not really the theory. The theory is coming from the foundations concept that assess your understanding, right? So questions 2 part B is the calculations. The whole questions for questions 2 is calculations. Part B evaluate your E field intensity and total charge. All right, and then part C is the Gauss law. Questions 3 Part A is theory. This is actually 3 marks for you. As long as you learn about the convections and conductions current, I already exposed the whole questions, then you should be able to answer that, right? Part B is the calculations on the parallel plate capacitor, right? This is chapter 6 in the textbook, right? I will touch a little bit concept on this. And then part C is the boundary conditions, right? You learn this a lot in the material space. For the calculations on part B, parallel plate is not much, it's only 6 marks, but there is quite a lot on the boundary conditions for 9 marks. So you expect a lot of calculations you have to perform on these 9 marks questions. Okay. Part C, questions 4, you only have 2 parts. Biot-Savart law is the calculations. It's actually very similar to your broadly defined problems, right? As long as you understand the basic concept, how to obtain the A file, and then how do you obtain the rho, then you should be able to answer that. If you have done your broadly defined problems yourself personally, you should be able to answer these questions, right? And then part B is the basic concept just to test your understanding. It's only 5 marks. So it's on the Ampere circuit law, right? And then last questions, part A is on the Maxwell equations, is about the theory. The theory means maybe we ask you to write out the formula, right, in the derivative form, in the integral form, and then you explain a little bit on each of the equations. We know that Maxwell equations, we have 4 Maxwell equations for the time varying field. Yeah? So it's not on the static, not on the electrostatic, not on the magnetostatic. It's actually the combined between them is time varying field. It's the final Maxwell equations that you need to understand. Okay, then we will touch a little bit on the Faraday law, right? This is also very simple calculations just to test your understanding. And the last part is the propagations. Propagations need you to understand a little bit of the basic concept on each of the wave propagations parameter. This one I will show you some example later. Okay, right? Okay, now let's move. We give an overview in general what you have learned the whole semester on the electrostatic and magnetostatic, right? And then in electrostatic, I introduced several parameters such as E field, right? Electric field intensity. And then I also introduce magnetic field intensity, this is comparable. One is on electrostatic, one is on magnetostatic. In electrostatic, in electrical field, you call this as electric field intensity. In magnetic field, you call this as magnetic field intensity. All right, one represent with E, one represent with H. The one with E field, you have the what we call unit as a voltage per meter, right? So you look at that voltage, how much voltage per 1 meter length, right? Same as well for the H field, you have ampere per meter, right? How much current per meter, okay? And then after E field, we also introduce several parameters which is quite related to E field and H field, which is D, right? Electric flux density. So pay attention on the unit, the coulombs per meter square, right? Is density. So how much charge in 1 meter by 1 meter area, right? And then you have the formula how this D relates with the E field intensity, right? You know that D equals to epsilon E, right? So this is the formulations which is relate the D in with the E field intensity. Okay, so on the magnetostatic part, you have capital B, which represent magnetic flux density, right? It's the same like D in E field, but in magnetic field, we use capital B to represent flux density. And the unit is Weber per meter square, right? But not only limited to Weber per meter square, or sometimes you can use Tesla. Tesla is represented by Weber per meter square. Okay, and how this flux density, magnetic flux density, relates with the H field. Over here, you have D equals to epsilon E. Epsilon is permittivity. But in magnetostatic, we don't use epsilon, right? In magnetostatic, we use mu. You know that mu is permeability. So we have B equals to mu H, right? Permeability. Okay, so this mu is equals to mu naught mu R. Okay, so these are the basic parameters that you need to know. Then let's look at electric permittivity, which is the constant with epsilon naught and epsilon R. And in magnetostatic, as I mentioned, we have permeability, mu naught mu R. Okay, so the constant you need to know. We per electric permittivity, we used to measure the electric polarizations of the dielectric. Okay, for magnetostatic, we used to measure the resistance of a material against the formations of magnetic field, right? So how much resistance we have in order to block the formations of the magnetic field. Okay, so then what is the in mu naught mu R? Mu naught is the constant in sorry, it's not mu naught. Mu naught is over here, yeah. Mu naught mu R. Same like epsilon. Epsilon naught epsilon R. Epsilon naught is the constant. Epsilon R depends on the material. Same as well. Mu naught is the constant. Mu R is depends on the material. Okay. So epsilon naught is 10 negative 936 pi farad per meter. Okay, or sometimes you want to use 8.854 times 10 power of negative 12 also can, right? So this is during the free space. This is the constant. And for the free space, when the electromagnetic field traveling in the free space, your epsilon R equals to 1, which means the special material we assume as a free space, then your epsilon R equals to 1. Okay, so same as well for magnetostatic. For mu naught is constant 4 pi times 10 power of 7, negative 7 Henry per meter. Okay, and then for free space, your mu R equals to 1. Okay, so these are the basic. And then in electrostatic, we introduce several laws. I start with the Coulomb's law, right? In magnetostatic, we have the same things as the Coulomb's law, which is what we call as Biot-Savart law, right? These two laws can calculate exactly the field of the electrostatic and magnetostatic, all right? But the calculations is a little bit of tedious. In order to calculate the Coulomb's law and also the Biot-Savart law, you have to calculate every single things. Okay. Then we comes up with another law which is simplified a little bit, and the Coulomb's law. Beside the Coulomb's law, we can also use the Gauss law, right? On the other side, we use Ampere's circuit law. All right. So these are the law that we use to calculate all the parameters involved. Okay. Then after we learn the static, we learn about the electrostatic, we learn about the magnetostatic. After that, we combine. We combine both of them together, and we call this as electromagnetic. Okay, and pay attention on here. When I mention static over here, electric field doesn't change with respect to the time. This is mainly refer to the time. As time change, electric field remain static. Same as well for the magnetostatic. As time change, magnetic field doesn't change, remain static with respect to the time. Okay, but when you combine together, as the time change, electric field and the magnetic field will interchange among them. Okay, so those are the overview. Those are the overview for the whole course. Okay, so let's go a little bit by little bit from basic, fundamental for each chapter. I will start with the Coulomb's law and the field intensity. In Coulomb's law, you know that in Coulomb's law we have 2-point charge. We start with the point charge, right? We have the 2-point charge, and then you want to calculate the force between them. You want to calculate the force between the 2-point charge. But of course, you need to know that there is a distance between the 2-point charge, because the distance will also influence the force between them. Okay. In general, Coulomb's law mentions that the force is a product of both charge, Q1 and Q2, right? So you multiply both charge. The larger the multiplications of the both charge will increase the force. If the smaller of the charge in between Q1 and Q2, you reduce the force. All right. So only two things. One is the force directly proportional to the product of Q1, Q2. And the second is the inversely proportional with respect to the distance square. Okay, with respect to the distance square. Distance is r, so r squared, which means your r or your distance increase, then your force will reduce. So inversely proportional, right? If you combine both of them, you will have k q1 q2 divided by r squared, and this k is actually the constant that you can calculate from 1 over 4 pi epsilon naught, and this epsilon naught is 8.854 times 10 power of negative 12 or 10 power of negative 936 pi farad per meter. Okay, so this all is the Coulomb's law between the two charge. If more than two charge, what you need to do? More than two charge, then you have to use the superpositions. You use the principle of superpositions, you sum all of them. So for example, I have Q1, I have Q2, and my test point is at Q, correct? So what is the total force comes from these two charge if I standing at this test point location? I can obtain the force comes from Q1, so which means you can calculate the force between Q1 and Q, your test point, right? And then you calculate the force comes from Q2 and Q, which you obtain another force. The total force will be force 1 plus force 2. All right. So these are the superpositions principle. Right. This is very easy. You calculate isolated each of them and then you sum together. All right. Then in Coulomb's law, you obtain force. What is the main idea we want to find the force? Because the force is not that useful for the electrical engineer. In order to obtain the force, the main idea is to find the electric field intensity. All right. So this is how what is the relations between F and E field intensity. All right, I will show you later. But from the Coulomb's law, from there I introduce from the point charge, then we can find the force or E field intensity for the line charge, for the surface charge, for the volume charge. All right. So for the line charge, you have rho L. This is what we call as line charge density, right? You have the rho L. How many coulombs in 1 meter, right? So your rho L is line charge density, coulombs per meter. And then if you want to find the surface charge, you get 1 meter by 1 meter, and you count how many coulombs inside that 1 meter by 1 meter. Don't care about the total area, because after that you can just multiply one part, the total area with the rho s, then you will automatically get the total surface charge. Right? That's why we introduce rho charge density. Okay, so 1 meter by 1 meter, you calculate how many charge we have in that surface area, then only you can multiply with the total area. So we call this as a surface charge density, coulombs per meter square. Okay, so same as well for the volume charge. You take 1 meter by 1 meter by 1 meter, a square in between them, which you can calculate the volume, right? So in 1 meter by 1 meter by 1 meter, or meter cube, we call this, and you count how many charge inside that, and we call this as a volume charge density. Okay, we call this as volume charge density, coulombs per meter cube. Okay, so from there you can easily calculate the E field intensity. You can easily calculate the E field intensity by just integrate whatever you have with the rho L, rho S, and also rho V. Okay, so that is the main idea we introduce the E field intensity and the continuous charge. Okay, then after that I introduce electric flux, another electrical parameters. What is actually electric flux? Which is the amount of the electrical field that penetrate the surface, right? For example, you have one charge, positive charge, You have one imaginary spherical surface. You close this with one imaginary spherical surface. And from there, you can easily calculate how much flux that comes out from that surface. Impossible. It's not practical for you to count each of the flux that come out from the surface, but you can use some replacement. We use another parameters, which is what we call as electric flux density. So don't get confused with C with meter square. C with meter square, which is same like the rho s, but this is electric flux density, not rho s. Yeah, but the unit is the same. So electric flux density, we have 1 meter by 1 meter. You count how many charge inside that. So for example, so you have 5 coulombs per meter square, and then from there you can easily convert. You can easily convert the E field and also the flux density. That is the relationships which I showed you before, right? E field and D. And at one point, this D is also called displacement current, electric displacement. Okay. Okay. Let me show you one example, quick one. For example, you have these formulations for flux density. So from this, you need to find out the volume charge density, right? Rho v. From here, you can easily find out the flux through the cube, which give you the range of the cube and the total charge enclosed by the cube. So how we can use these informations to the capital D, which is flux density, to find out all these three informations. All right, a quick one. The first one, rho v. So rho v at -1, 0, and 3. One very important Maxwell equations, rho v equals to del dot t. The meaning of del is partial differential. Partial differential, which means you differentiate with respect to x, differentiate with respect to y, differentiate with respect to z. Okay, so which means at this point, this ax, you only differentiate at this part. Another dy, you differentiate with respect to this, and dz you differentiate with respect to this component x. Okay, so you can easily find out what is rho v then. Okay, so at this part, you see this part, there's nothing related to x, then you get a 0 when you differentiate. There's nothing related to z, you get 0, right? But this y, you have 4xy over here. So after you differentiate, then you have 4x. Once you have rho v equals to 4x, then you replace into here. Your x is -1, right? So then your rho v -1, 0, 3, you just insert into here, then you get the answer. Okay, so this is how you obtain your rho v. And then in order to obtain the part B, you know that in Maxwell equations, flux equals to Q enclosed, and also integrations rho v dv, right? So you have the range of the cube, which means you have to integrate all of them, right? 0 to 1, 0 to 1, 0 to 1, 0 to 1, right? And then you know that your rho v is 4x, and your dv, because the cube is represented in Cartesian coordinate, So you put it dx dy dz, all right? And then you split into each of the component, right? You split into each of the component, those constant you take out, and then you integrate. So easily you can find out your flux. So that is the total flux, which is equals to 2 coulombs. All right. And part C is easy because your Q enclosed equals to flux, then the total Q enclosed is equals to C. Okay. That is how we find uh, the information from the flux density. Okay. Right. Then after the flux density, we have the Gauss law. But before I go into the Gauss law, is there any questions? Am I going too fast? Are you able to follow? Right, but this is all the just the normal revisions. Are you okay with that, guys?
All
But
good.
okay,
Okay, like
Good,
that.
good, good.
okay. So if you have any questions, you can put it in the chat box. Okay, then let's move to the Gauss law, right? From the Coulomb's law, we move to the Gauss law. So in Gauss law, in general, we have two form. We have two form of the Gauss law. One is the integral form, and another one is the differential form, right? So the integral form, we have closed loop integral d dot ds, right? Which is I shows what I just shows you, rho v dv. That is the integral form, and the differential form is rho v equals to del dot d. So this is also the one that I shows you just now, the volume charge density. Okay, so that is the Gauss law. Then in Gauss law, we can apply this to several parts, same like the Coulomb's law. You can apply on the point charge. You can apply on the infinite line charge, right? And you can also apply on the infinite surface charge, right? And also you can apply on the uniform sphere charge. Okay, so these are uh, uh, the the applications of the Gauss law. Uh, the slide I will share once we complete it. So I want you to focus during the class first. After that, I share in the group. Don't worry. Okay. Right. So the applications of the Gauss law is a lot, but for these revisions, I will just pick one which is related to the infinite uh, piece of the charge, which on the surface charge, yeah, on the surface charge. So we choose the rectangle one, right? This is the infinite large surface. Okay, so infinite large surface. If you want to find the flux density and also the capital, also the E field intensity using the Gauss law, what you need to do, you know that the surface is full with rho s, right? You know what is the rho s, coulombs per meter square, right? So from the surface charge, you have those uh, electric field or flux density that comes up uh, orthogonally or normal to the surface, and this is flux density that's come up from the surface, normal to the surface, or 90-degree to the surface. All right. So the directions of the flux density is only dz-az. Why we have the dz-az only? Why not x and y? Why not X and Y? I will I will show you why we don't have X and Y in this case. Yeah, but in since this is rectangle uh, form of the field, uh, we choose the rectangular box, right? We choose the rectangular box to fulfill the symmetrical properties. So this, for example, if I choose this rectangle box, right? I take it out like this. So the area over here inside the rectangle box, and my charge is the Q equals to rho S A, right? Rho S is flux, surface density, surface charge density, and A is the area, right? If I multiply my rho S with A, then automatically I know how much charge inside this area, right? So I know that there is a D in this case, and there is also on the side. So in this case, I just mentioned that there is no X and Y component because when your D is not tangent, is not surface to the your D is not normal to the surface, automatically you don't have the you have the zero, right? For example, your D on the X and Y is automatically zero because there is no normal to the surface. In Gauss law, only those components now normal to the surface will give you the impact. Those tangents to the surface is zero, right? So that's why you don't have AX and AY. So in this case, you have your Q equals to closed loop integral d dot ds. So in this case, only you calculate. Okay, so you know that your Q is rho S A, then your DZ, your A is above both side on top and the bottom, right? Your ds from top and the bottom. So automatically you have the both A. So in order to find dz, so you can put it here and you cancel out the surface, and you have your dz equals to rho s divided by 2. Okay, so your total d is rho s 2 az, and in order to find E field intensity, you just use the formulations. So you can notice that when the surface infinity large, your E field and also your flux density doesn't care about the area anymore. All right, because over here you already cancel out the area. So you only care about how much charge, then surface charge density. Then easily you can calculate the E field intensity if the surface is infinity large. All right. So that is the basic for the applications of the Gauss law on the surface charge. Okay. Then after electric field intensity, you been introduced with the flux density, and then the next one is the electric potential. So electric potentials is another parameters which we always use, which represent with V, potential difference, right? But before you obtain the potential difference, which is VAB, what is the difference between the 2 points? Right? What is the potential difference between the 2 points? If you take only 1 point, then you have one potential. You take another point, you have another potential. Then the potential difference between the 2 points, which means you have to minus VB minus VA, right? But before you obtain the potential difference, definitely you need to know the electric potential energy, W, which is the total work done in moving one charge from one point to another. This is potential energy. All right. So, uh, in point charge, we choose reference as a zero because VB minus VA, we usually choose the reference point VA as infinity. When you choose VA as infinity, you have your VA equals to zero. When your VA equals to zero, then you can easily find out your VB. Okay, so that is the main thing. So the formula in order to find out the voltage or the potential is V equals to Q divided by 4 pi epsilon naught R. This is the potential difference if you choose your reference point as infinity. Okay, but if you don't have infinity reference point, right? If you don't have infinity reference point, then you have to calculate. You have to calculate the C, or you have, if you have more than one point charge, you need to use the superpositions, same like the Coulomb's law, right? You need to calculate each of them and just sum together. Okay, right? So this is point charge, and then if you extend it into the line charge, then it's the same. It's the same. You just integrate rho L with dl, and the rest is the same. Okay. So point charge, line charge, surface charge, volume charge, everything can be extended from the continuous charge distributions, as I mentioned before. Okay. But pay attention. If the reference point is infinity, your formula is V equals to Q divided by 4 pi epsilon naught R. Other than infinity, you have C, which is the constant. Right? You need to find out the constant, which is to determine the chosen point of the reference. Okay. So, in order to find the potentials, if you know the charge distributions, you use this. If you know your E field, then you can use the relations between E and V to find out, right? To find out the potential. So easily you can find out VAB equals to VB minus VA. Okay, so that is on the potential side. Okay, so the whole total topic which we cover in electrostatic is just until electric potential. Okay, after that, we extend it a little bit to another topic, but that is the applications part. But so the electrostatic is until here. Okay, right. Then from the electrostatic, we extend it. We extend it and we see how the behavior of electric field in the different material. Okay, so in this part, I introduce several property. Three materials according to the electrical behavior and the features. One is on the conductor, another one is on the semiconductor, another one is on the insulator. All right. So the electrical parameters in this material, you know that there is different types of the behavior, right? But I will show you this later. But before that, let's take a look on what is the difference between convection current and the conduction current. Okay. The definitions of the current, which we call how much ampere uh, how much charge that passed through the area in a certain time. That's why you have your I in this case, your I in this case is how much changes of Q or charge with respect to the changes of time. All right. So you can measure from one end to another end, and when the current, when the charge move, the current appear. All right. When the charge move, the current appear. Without the charge moving, you don't have any current. Okay, so that's why the informations of the definitions of the current is del q with respect to the del t. Okay, and the if you want to calculate the total current, you can use the current density, which represent is in J, right? Ampere per meter square. It's the same like the all the density which you learn, but this one is the current density. So, uh, for example, the cable you have over here, the total current that flow into the cable is dq over dt, right? If you don't want to calculate this, then you can use the current density J, all right? So if you have exactly normal to the surface, your current, or you have not normal to the surface, then you can easily calculate the J. And then once you calculate the J, you multiply with the surface area, then you obtain the current, right? Same as well on the not normal informations. Okay, so that is on the uh, current, and then you move to three types of the current, which introduce convection's current density, conduction's current density. Another one is the displacement current density, right? In properties of the material, we look at these two current, but in Faraday law, we have current displacement current density. Then the convection's current density, we have several criteria. Number one, not involve conductor. Convection's current not involve conductor. All right. Second, it doesn't satisfy Ohm's law. We don't use Ohm's law in convection's current. Okay. And the third one, the current flow through insulating medium such as liquid, gases, or vacuum. Right? So these are the convection's current. These are the convection's current. All right. So the example of this convection's current is like the beam of the electrons in the vacuum tube, right? Your CRT monitor, your X-ray, your home ventilation systems from the aircon, all these is called as the convection's current, right? It's called as the convection's current. Then we move to the conduction's current. Conduction's current is the normal current that you learned before. It requires the conductor, all right, and is characterized by the large amount of free electrons. Because why you need free electrons? Because the free electron is moving. When the free electron is moving, then you produce the current, all right, and these free electrons provide the conduction's current due to E field, okay, and it satisfies Ohm's law. So this is what we call as the conductions. Okay, so that is the two types of the current which we focus: conduction's current and the convection's current. One required conductor, another one doesn't require conductor. One flow in the conductor, another one flow in the conductive gases, and so on. Okay, one satisfies the Ohm's law, another one doesn't satisfy the Ohm's law. All right. Okay, then let's take a look on the conductor material. There is several informations that you need to know for the conductor. Okay, so for example, I have one conductor. This is the isolated conductor. All right. Then I apply the E field through the conductor. Right? Apply the E field, external E field through the conductor. What happened when I apply the E field through this conductor? So inside the conductor, there is a positive charge and negative charge. When apply the external field, external electric field, the charge will start to move, or we call this as migrations. Right? So this charge move quickly, the migrate. So positive charge will move according to the directions of the E field. The positive charge will move directly, quickly to the directions of the E field towards this part. All right. And on the other side, negative charge will move opposite directions to the E field, external E field. All right. So what happened in this is when there is a charge that appear on the surface, right? This free charge do two things. One, the accumulated surface charge will form induced surface charge, right? The charge that accumulated on the surface of the conductor, they will form induced surface charge. And this induced surface charge will set up an internal induced field, which we call this as EI, internal E field, right? Because just now when I apply external E field, then automatically internal E field will form according to these free electrons. All right. So when you produce this E field, the amount of the internal and the external will be the same, and it will automatically one on another directions, another one on the different directions. Both directions will cancel out each other. And this is the very important property of the conductor. What happened when they cancel out each other? Which means a perfect conductor cannot have electrostatic field within the conductor. All right? Then you don't have the electric field intensity, you don't have the rho V, you don't have the potential difference inside the conductor. Okay? So this is very important for the properties of the conductor. Okay, right? Okay, then let's move on to the boundary conditions. Boundary conditions, the main idea is to look at when the electric field move to two different types of the material. Okay, when you move to the two different types of the medium, right, what will happen? So in boundary conditions, we have go through three conditions. One is different types of the dielectric. One is the conductor and the dielectric. And another one is the conductor and the free space. Right. So these three different types of the conditions. Okay. But in order to obtain these boundary conditions, you have to use the Maxwell equations, right? The Maxwell equations, which you have learned, closed loop integral E dot dl equals to 0, and closed loop integral D dot ds equals to Q enclosed. This is the Gauss law. We learned these Maxwell equations. And then you have to pay attention. They are component. component of E field. E field, you have two components, right? Component of E field. One component is the tangents component. Another component is the normal component. All right. So tangents component combined with the normal component, you will have the total E field. Same as well for the flux density. Flux density D also have two types of the component. One is D tangents, another one is D normal. Right? When you add up together, you will have the total D. Right? So your E will be combined with ET tangents plus EN normal component, and your D also same. Tangents and normal component, you combine, then you have the flux density. Okay, but in total, in summary, these are the one. So if your electric field propagate through different types of the material, right? Dielectric to dielectric, so your E field will be the same. Your dielectric will depends on your another one. Your tangents component will be the same, but your normal component will be different according the types of the material, epsilon 1 and epsilon 2. All right. Same as well for the flux density. Normal component will be depends on this one, right? And your tangents component will be depends on the types of the material, right? So the rest is also same. Conductor to dielectric, then you have these. Conductor to free space, you have this. I suppose the behavior of this component is also included into the formula. You can check, right? If don't have, then you have to understand this, right? Okay, right? So the boundary conditions that we have looked at these then being applied to the resistance and capacitance. In this one, I don't really go into details during the semester because as you already learned in your electrical principle 1 and electrical principle 2 about the resistance and the capacitance, right? But these are the applications of the boundary value components, right? So for today revisions, I will just focus on the capacitance, right? What I focus on the capacitance is on the parallel plate capacitance. The parallel plate capacitance, which means you have two surface area in the rectangle, right? And in order to find the capacitor or capacitance, what you need to do is you need to know the charge divided by the voltage that you apply. If you don't know the charge, and you can easily find out this with the uh, assumptions of these formulations, epsilon multiplied with the surface area S divided by the D. The D is the distance between the two plates, the distance between the two plates, right? So just like this, right? So if you apply the voltage on this parallel plate capacitance, then you should be able to calculate the total capacitance. Now, this is the example. For example, I have two different types of the material, epsilon 1, epsilon R1, epsilon R2. Epsilon naught is the same, right? Because it's the constant. Epsilon R1 depends on the material. Epsilon R2 depends on the material. Okay? And then the total distance between these is D divided by 2 and D divided by 2. This is the total distance over here, right? So if you have epsilon R1 equals to 4, epsilon R2 equals to 6, your D equals to 5 millimeter, which means over here is 2.5, over here is 2.5 millimeter. The surface area is 30 centimeters square, right? Now, the questions ask you to find out the capacitance, right? In capacitors, you learn in electrical principle 1 and 2, you learn capacitance, if connected in series, what is the formula? Capacitance connected in parallel, what is the formula? It's actually opposite with the resistance, right? If series, you use the formula of parallel. If parallel, you use the formula of the series. It's just opposite with the resistor, right? So the solutions is straightforward. You can easily count what is the uh, formula capacitance just by using this formula. You can calculate that, you can calculate, and you obtain one capacitance over here, another capacitance over here. So if the question asks you to find the total capacitance, since these are the two material which is connected in series, your capacitance is connected in series, right? Then you use parallel, right? You use the parallel. So in resistance, this is the parallel formula, right? But how do you calculate if the capacitance more than three, more than two? This only you can calculate in parallel if two. But if you have three capacitance, then you need to use the parallel 1 over C to calculate that. All right. So this is how you calculate the total capacitance with respect to the types of uh, the the how the capacitance connected, right? So in uh, in series like this, you use the formula for a parallel, same as the resistance. Okay. Another type is like this. Another type is actually the capacitance connected in the parallel, right? The capacitance connected in the parallel. Then you can calculate with the series formulations. Okay. So it's just series and parallel, which you have learned in electrical principle. Okay. Now, so that's all for the electric field boundary conditions and also the applications of the boundary conditions. Okay. So we have done on the electrostatic part. You have any questions? Let me know if you feel confused at which part which required further explanations. Okay? Ada tak?
Doktor,
Ya.
yang S tu kenapa kena bagi dengan 2?
Oh, tak sebab yang ni sebab yang ni. Sebab dia punya distance ni sama je dengan yang ini kan. Dia punya D tu dia bahagi dengan 2 sebab dia punya distance tu. Right? So total ni 30 ni adalah dia punya total. So bila you nak calculate one part, then you divided by 2 lah sebab dia punya area ni adalah total 30 cm square. Okay?
Okay, Doktor, thank you.
Right. Okay. So you don't have any questions on the electrostatic. So let's move on to the magnetostatic. In magnetostatic, we have two big law that you learn. Same like the electrostatic, you learn Coulomb's law, you learn Gauss law. In magnetostatic, you learn Biot-Savart law, which is equivalent to the Coulomb's law. Another one is the Ampere circuit law, which is equivalent to the Gauss law, right? So in Biot-Savart law, is used to understand the magnetic field affect the moving charge. We want to understand how the moving charge that create the magnetic field. And in Biot-Savart, you only have three formula. This is the complete formulations for the Biot-Savart law. All right. For the Biot-Savart law, you have I, you have 4 pi rho, you have alpha 2, alpha 1, and you have A phi. And you need to know that the A phi is actually comes from the directions of the lines of your current flow through the line and the 90 degrees directions from the current to the test point. Okay. And then if your line is infinite large or long, then you use these equations. Okay. You use these equations. So you have only two equations. One is on finite length, one is on infinite length. So the rest is just you need to know how to identify the directions of the magnetic field by using these informations. All right, cross multiplications is a must. If you don't know how to perform cross multiplications, then you won't be able to solve any problems on the magnetostatic. Same as electrostatic, right? Okay, that is on the Biot-Savart. On the Ampere circuit law, one more thing. On the Biot-Savart, try to look at how you obtain your broadly defined problems. I will share the solutions of broadly defined problems after this, and see and check back your answer with that. I think I will close the broadly defined problems submissions after the class. So you once I share the solutions, you won't be able to submit anymore. Yeah. Okay. So Ampere circuit law. Ampere circuit law. What we means by the Ampere circuit law is actually the same with the Gauss law, but the main problem is you can find the total current or you can find the total magnetic field intensity, either one. Okay, so you can use the Ampere circuit law to find each of them, either one of them. So for example, if you have the current flow, so you have the magnetic field, right? You have the magnetic field that generated, then you know the current distribution is symmetry, and if the magnetic field is known, then you can find out the current. If the current is known, then you can find out the magnetic field. Okay, so that is how you can use the Ampere circuit law to find either of them. Okay, so just use this formula. Closed loop integral H dot dl equals to I and close, which means you can determine magnetic field intensity given a current or determine current given a magnetic field. So in infinite line current in Ampere circuit law, right, one of the applications is the infinite line current. So you have infinite long line current. Okay, so by using the Ampere circuit law, you can easily find out what is the current. Okay, but you need to know how to choose the coordinate systems. So since this is the circular type, we choose the cylindrical coordinate, right? So dl will be rho d phi a phi. Okay, so then you put it inside using the cyclic permutations. A phi dot a phi equals to 1. Then the rest will be like this. All right, so if the line is infinitely long, you can use these informations for the Ampere circuit law, and which is the same as the Biot-Savart law when if this is the formula which is the same like the Biot-Savart law for the infinite long line current. Okay, so that is applications of the Ampere circuit law. Another one is the infinite long coaxial transmissions line. So what is the difference between the infinite long current is the transmissions line, the coaxial cable, you have different types of the area, right? You have different types of the area, and in this case, they will ask you to find out H, what is the magnetic field everywhere, which means what is the locations at which part, what is the magnetic field. Okay, so 4 positive regions and 4 ampere path according to the situations, depends on the situations that you have, right? So in coaxial cable we have 4 different locations, right? And then you have to find out each of them by using the Ampere circuit law, right? What is the total magnetic field intensity at these 4 locations? Okay, so using the Ampere circuit law, everything is you can perform as usual, right, for each of the locations, right? I don't go into details on this part. So the main thing is you understand the concept. The magnetic field intensity is different according to the structure of the transmissions line. Okay, all right. So these are the example of the applications on the transmissions line for coaxial cable. Okay, now, so in total, overall, you will have these functions of the H field from your rho is from 0 to A, this is your H field, A to B, this is your H field, B to B plus T, this is your H field, and another one is 0. Okay, so that is on magnetostatic. So for the magnetostatic, we will just focus on 2 things. One is Biot-Savart law, one is Ampere circuit law. That's it, right? We don't go into others part. Okay, for the after that, let's move to the combined part of the magnetostatic and the electrostatic. We combine together, which we produce the Maxwell equations, right? So these Maxwell equations, you have the static and the dynamic. You just focus on the dynamic part. 4 Maxwell equations, 2 different form. One is on differential form, one is on integral form. Okay, so Gauss' law is the same, never change, right? Non-existence of the monopole, which means your magnetic field cannot divide into north and south, is always must have north and south pole, right? That's why over here is mentions non-existence of the monopole. These 2 things is the same, all right? And then after you introduce the Faraday law, will be slightly different. Del dot E, del cross E equals to negative del B over del T. What we means by this Faraday law formulations is you can easily find out the electric field intensity with the changes of the magnetic field with respect to the time. All right, from the formula you can easily find out. Once you look at the formula, you know that, oh, when the magnetic field change with respect to the time, we produce the electric field. All right, that is the Faraday law. And then for the Ampere law, is slightly different because you add one small terms, which what we call as the displacement current. right? This is the one that we add in to cater the behavior of the displacement current. Okay, so this is differential form. Okay, and the same for the integral form. The same for the integral form, just the way they write is a little bit different, right? But the concept is still the same. Okay, so the one that we make the big change is actually comes from the Faraday law. What we need to know on the Faraday law, I will just introduce the complete equations over here, which what we call like this, right? I introduced Faraday law previously with three conditions. One is the transformer EMF, another one is the motional EMF, and the last condition is actually the motional EMF plus the transformer EMF. And this is the total equations for the combined EMF, which we produce. All right. So from here, you can easily find out, depends on the conditions, which is moving. Magnetic field is moving, or the electric field is moving, or both is moving. All right. So then you use the proper equations. This is integral form. This is differential form. Okay. And then for Faraday law, I think this one is you learned before for the transformer, right? You learned before on the VEMF you can generate according to the Faraday law, right? You generate the voltage over here, and you have another one. You generate another voltage over here according to the numbers of coil. This is primary coil, this is secondary coil. So for example, N1 is 500 coil, you generate different types of the voltage. Another part is 300 coil. So 300 coil, we will generate another VEMF. Okay, and this is how you can calculate the step up transformer, step down transformer from this control of the coil. All right, so you can easily find out the voltage that generated comes from the coil. Okay, another things beside control the number of coil, you can also do one things, which is control the changes of the flux. If you look at these equations, yeah, d phi over dt, which mean the changes of the flux you can control. How do you control the changes of the flux? Which mean you use either you use the current element, you move the current element, or you move the magnetic element. All right, then you can control the changes of the flux. If I make a little bit of changes, for example, the magnetic flux through the coil change from 0.5 Weber to 0.94 Weber in 3 seconds. What is the induced voltage in this coil? If you have the number of coil is still remain at 500, but now the changes of the flux is different. Assume that this magnetic field is moving upwards and downwards, is moving, right? You have the coil, but this one is moving. So if this magnetic still is moving up and down, you change the flux. So what is the changes of the flux? The changes of the flux will be d phi over dt. So the changes of the flux is 0.5 to 0.94. So which means you just use 0.94 minus 0.5 divided with 3 millisecond. Right? This is d phi over dt. And then you just multiply with n1 500 equals to negative n1 multiplied with d phi over dt. Then you obtain the VEMF in that respected coil. Okay? Right? I hope it's clear on this part. All right. That is Faraday law. Okay? And the last part is the wave propagations, right? The wave propagations, there is not much calculations which is confused. I don't think you need to perform any integrations or differentiations. The only thing is you plug in the formula. Right? So in the summary of the wave propagations, we have different types of the medium. How the wave propagate in different types of the medium. The one thing is how the wave propagate in the free space. All right. And then what is the criteria, what is the characteristic? Like the conductivity is zero. Of course, when your wave propagate in free space, you don't have the conductivity, right? And your epsilon is only equals to epsilon naught, which is the constant, because your epsilon r equals to 1. Your mu is also mu equals to mu naught, because your mu r equals to 1. Okay? And then what about when the wave propagate in lossless dielectric? So if lossless dielectric, your uh, conductivity is still equals to 0, but your epsilon, you must take into the considerations of the types of the dielectric. In this case, you usually given mu r, how much is the mu r for that particular dielectric. Same as well for the epsilon and mu r. Mu r also given, epsilon r also given. And if you find out the value of the conductivity should be much more less compared to the tangents. This one, omega and epsilons, right? So this is another parameters. Then if your medium is lossy dielectric, your conductivity is not equals to 0, right? And then the rest is depends on the material. And if your wave is propagate at the good conductor, what will happen? Your conductivity is infinite. Your epsilon is equals to epsilon naught. Your mu is equals to mu r mu naught, but your conductivity should be much more larger than omega epsilon. Okay, so this is the summary of the medium that your wave should propagate. So in this case, when your wave propagate at two dielectric, different type of the dielectric, one is perfect, which is lossless, less loss. We assume this is perfect dielectric. You shouldn't have conductivity in the dielectric. All right. For imperfect dielectric, which means you may have some of the conductivity that flow in the dielectric. Okay, I will show you the final. Let me give some. Okay. Okay. If you still remember, I give you 4 questions, 4 questions from the last lecture. I ask you to try on that, and I will give you the solutions. But look at this. Look at this. I will give you the overall idea how to solve that 4 questions. So several parameter which is important, right? The first one is the gamma, which is what we call as propagation constant of the medium. Gamma is equals to alpha plus j beta. In these equations over here itself, right? This equation itself, we have 3 very important parameters. The gamma is the propagation constant of the medium, which is per meter. The unit is per meter. And then we have alpha. The alpha is actually the attenuation factor. Attenuation factor is how much you lost. Right? For example, if you transmit 5 dB, if your alpha is 5 dB per meter, which means you lost 5 dB in 1 meter. If you transmit for 10 meter, then you lost 10 dB, or which means 5 dB per meter. 10 dB is 10 dB per 10 meter, per 2 meter, right? So this is the attenuation factor. Another unit is Nepper per meter for attenuation factor. Another parameters is phase constant, or we call this, sometimes they call this as a wave number, radian per meter. So the wave number, the formula is omega, right? And then you have the big square root over here, which inside you have mu, you have epsilon divided by 2, and inside you have a small square root 1 plus epsilon 1 plus, this is sigma conductivity divided by epsilon multiplied with omega and square and plus 1, right? But I think this formula is inside your formula worksheet, which will be given during your final exam. So you don't have to memorize, but you need to know how to calculate that, right? You need to know that. Okay. And then, okay, this formula is for the attenuation factor. You can use this formula to calculate the attenuation factor. It's slightly different with the phase constant. Look at this. All right, what is the difference? The only difference at -1 and +1. 1 for attenuation factor is -1. For the phase constant is +1. All right. So bear in mind, look properly how you can calculate that formula. And then the fourth parameters is this eta. Eta is actually represent intrinsic impedance. It's actually the ratio between the electric field divided by the magnetic flux density. All right. So the intrinsic impedance, the unit is ohms, right? Because impedance, right? So you can find out this eta by using the magnitude, right? Because you have the magnitude and also the theta, the angle. To find the angle, you can use tangents to theta, which is sigma divided by omega epsilon. To find the absolute eta, you need to use this formula, right? But everything is, I think, inside the formula sheet. All right. And then you have the loss tangent. The fifth parameters is the loss tangents. Sometimes they use 2 theta, sometimes they use tangents theta, but the formula is sigma divided by omega epsilon. This is loss tangents. Based on the loss tangents, you can easily identify how lossy a medium. If tangent theta is very small, this is considered as a good dielectric compared to the conductivity. If your tangent theta is very large, this is good conductor. All right. So based on the loss tangents, you can identify the types of the medium in the electrical parameters. Okay. So, and then the rest is just the parameters. We have wave velocity. This is u. Wave velocity is just like c. C equals to f lambda, right? But this one is wave velocity is just like the speed of light, because c is propagate in the free space. But when your electromagnetic wave is not propagate in the free space, then you have a little bit slow wave velocity, which propagate with different meter per second, right? Your c is 10 power of 8. I can't remember what is the constant, 10 power of 8 meter per second, right? So your u is slightly different, depends on the wavelength and also the frequency. Okay, and then you have another parameter lambda, which is the wavelength. This is very common, 2 pi over beta, right? The beta is the phase constant. And then you have omega. This is the 2 pi f radian per second, which you learn in electrical principle 2. And then you have complex permittivity and also the permittivity. So this one, if you notice that there is a complex permittivity, then you can use these equations. If you have permittivity, you just use this event. Permittivity is what you learned before, right? Epsilon equals to epsilon naught epsilon r. Permeability is what you learned before. Mu equals to mu naught mu r, right? So the rest is normal. Okay. Now, another type is the general equations of the wave propagations. Okay. Now, look at this. This is the electrical field formula, and this is the magnetic field formula. These equations give you the wave propagate at the positive z directions. Okay, so that's why you have this electrical field functions at the z-axis with respect to the time. Right. So this one, look at this. Z is the directions of the propagations. The directions of the E field, the directions of the E field is at x-axis. The directions of the H field is at y-axis. So they were always orthogonal to each other, but they won't be able to have the same axis. So one axis on the E field, one axis on the H field, another axis is the directions of the wave propagate. Okay, so this one I showed you before in the previous slide. Okay, right? So you have to go through, try to understand how you can use the formula, right? And then let's take a look on the questions. Usually the questions in this chapter is just nothing. You just look at the questions, obtain the informations, right? And then you find out all the parameters required using the formula. You just plug in the value into the formula, right? Just like this one. Questions 1 from the previous questions given to you. right? I already solved everything. I will give you the solutions and just try to understand the solutions, and usually the question is more or less the same, right? You just plug in the informations into the formula. So for this one, loss tangents, right? Loss tangents, you know that this one, uh, conductivity divided by omega epsilon, right? So the first thing you need to do, you extract all the informations given to you: frequency 200 megahertz, mu equals to 5 mu naught, epsilon equals to epsilon naught given in the questions, and beta equals to 10 radian per second. This is the phase constant already given to you, right? And then given to you the wave number. The wave number is the phase constant, right? As I shows you over here, right? Phase constant or the wave number, radian per second. So you have all the informations, then you try to look at, okay, what is the loss tangents? The loss tangents in this one. This is the one that you need to find out, okay? Then you know you have beta equals to 10. The formula for beta is using these informations, this formula, all right? So you can easily find out, the rest of them, because this one, if you look at this is actually the loss tangents. And if I assume this one is the one that I want to find, I can assume it as x. So I replace this as x. Then the rest you can find out. You know you have the mu, you have the epsilon, so you have the beta, you have the omega, right? 2 pi f. F is 200 megahertz. Then easily you can obtain the x, and which is the loss tangents. Okay, right? So this is how you can find out the parameters. And then the next one, they ask you to find the conductivity sigma. So the sigma, you know that your loss tangents is this one, and then from your loss tangents you can easily find out this one, right? Omega and epsilon, you know, then easily you can find out your sigma, how much. And then number three is, would you classify the material as lossless or lossy? Lossless or lossy depends on the loss tangents. You have the sigma. Your loss tangent is this one, right? Omega epsilon. So this is your sigma, this is your loss tangent. Which one is much more larger? So if you can find out this, then this is definitely the lossless material. All right. And then the rest I don't want to go through. Attenuation constant, complex permittivity, intrinsic impedance, all this is inside the formula. You just plug in, and you don't have to do anything. You just plug in and calculate, right? It's very straightforward. And you can see the calculation is short, concise, right? You don't have to do any integrations and differentiations. All right, so I think that's all what I want to cover, and I would say 90% already covered for the final exam questions. The 10% is actually also inside, but it is not exactly in as the one that I discussed. So it depends on your understanding. Okay. Right. So you have any questions? But before that, I want you to spend some time to help me to evaluate the spark. Is it so hard for you to evaluate the spark? Just for a while. Log in and evaluate it. I don't think it's hard for you to evaluate the spark. It's just 5 minutes, I think. Why is so hard for you to evaluate? Let me check. How much is it? You see, until now, there's only 67 and 75% for sections 1 and sections 2, and I can't see on section 3 because it's under Dr. Norazmi, but you have to evaluate as well. You see, for 46 students who register with section 1, only 67% that evaluate the spark. Please, I need you to evaluate it because this is part of your responsible, right? The evaluations of the lecture teaching, it will help to improve the quality. Not only my course, you should evaluate every course that you have according to the lecturer performance. All right. So about the coursework, if you have submitted everything, then it's okay. Those who submit, usually I will give the marks, and if you don't submit, I can't do anything. You lost the marks. I will give the total marks once I finish all the marking, right? For test 1, test 2, I guess you already obtained the marks in the author. You can check on that. Also, I will share all the answer of the tutorial and the quiz in the groups. Okay? You have any questions?
No, sir.
Guys? Ada soalan? Diam je.
Brother. Pasal boundary tu, bukan boundary, fire server tu, current flow tu saya nak tengok macam mana tu. Saya masih lagi buntu.
Current flow tu,
Yeah.
current flow tu
Dia
usually dia bagi.
dia macam contoh Z tu kosong lagi kecil pada Z, dan Z tu lagi kecil pada 2 ampere. Ni dia punya flow tu ke bawah lah daripada arah Z tu.
Kena tengok dia punya flow of current tu dia kata towards ke mana. Kalau dia kata positive Z axis, then which mean dia bergerak towards ke positif lah. Kalau dia kata current flow tu flow towards negative Y axis, which mean dia current flow dia dari Y bergerak ke negative Y axis. So depends on the question. Selalunya dia questions bagi lah. Okay. Okay, the BDP solutions, need to know that we can have time to submit the BDP before to close the submissions. What time you all want me to close the submissions? Because selagi saya tak close the submissions, saya tak boleh share the solutions. Kalau saya dah share solutions, means saya kena close the submission lah. Tapi you need that solutions untuk study jugalah, sebab I would say if you can do the BDP, that will help you on the final exam. So what time you want me to close the submissions? Can I close? Ramai lagi ke yang belum submit? Sepatutnya you dah submit semalam kan? Sepatutnya lah. Sebab saya dah extend a little bit sebab saya tengok ada yang belum submit lagi. Tapi bila saya nak close the submissions, right? Kalau saya habis the class, saya terus close the submissions, okay ke? Okay tak? Boleh right? So
Sir,
yes,
pukul 1 boleh tak?
satu. Belum siap lagi ke?
Tak, saya ada last tu.
Boleh lah.
Okay, thank you.
Right. Okay, so 1 o'clock saya close the submissions, lepas tu saya share. Okay guys, so
Doktor,
yeah.
saya nak tanya doktor pasal yang tadi tu, yang Maxwell equation. Doktor kata yang kita teori tu belajar kita kena fokus pada bukan yang dynamic statistic, fokus pada yang vary lah doktor, time variant lah.
Yes. Maxwell equations memang untuk yang time variant, yang final one lah, yang bukan yang static, yang final.
Okay.
Right. Okay, right. Ada lagi soalan? Okay, so kalau tak ada, saya end the class. So esok kita jumpa pukul berapa esok? 9 So 3 hours. So kalau you habis, tapi close book lah esok Formula tak perlu bawa sebab memang ada dalam soalan. So you just bawa pen dengan calculator je. Okay, so I see you tomorrow. All the best.
Okay sir, thank you.
Thank you, doktor.
Thank you very much.
Thank you, doktor.
Terima kasih doktor, terima kasih banyak doktor.
Thank you, doktor.
Thank you, doktor.
Thank you doktor. Terima kasih doktor.